name is Dinakar. So we had a very interesting keynote in the morning where, one of the things that came out was friends don't let friends edit Docker files. And this session is going to be all about editing Docker files. So if you run into any issues with tools producing Docker files and you're having to debug that, hopefully this session is going to be helping you out in that context, okay? So just a quick thing about myself. So I'm the maintainer of the AdoptOpenJDK Docker Images. I co-maintain that along with Martin and George out here. I also work on OpenJ9 and do a bunch of cloud optimizations. So I'll be talking about that as well out here today. So the way that I wanted to do this talk was, it has a bunch of slides, but also demo. Sorry, you have it. Okay. Yeah. Okay. Is this better? Okay, great. I guess. So yeah, what I want to do is, I have a bunch of slides, but also a demo that you can take a look at. So it's on GitHub. That's my ID, DINOGUN, and what's in Spring Boot. So all of the stuff that I'm going to be talking about, the Docker files and so on, everything should be available on GitHub out here. I'll be showing this link later on as well. So I thought I'll just quickly touch upon AdoptOpenJDK. So how many of you here are using AdoptOpenJDK or aware of AdoptOpenJDK? Okay, very few hands. So AdoptOpenJDK is a community that produces pre-built OpenJDK binaries. So we have a huge build farm. So all of these companies that I've listed out there support that, and I think I should be okay. I think that this is probably not a comprehensive list. I prepared this a while ago. So more and more companies are joining in all the time. Those are all the architectures that are supported. So we have a huge build farm, all these different architectures that are supported, and we produce OpenJDK binaries that are, you can use REST APIs to be able to just, download them. And we also produce Docker images. So we have both the official and the unofficial Docker images. The official ones, of course, maintained by Docker. There are a few operating systems that are supported from the official Docker image perspective, and a whole bunch of other operating systems that are supported in the unofficial Docker image repo of AdoptOpenJDK. So if you're looking to containerize your application, so this would be a good place to start, I would say, from Java Docker perspective. So how many of you here have containerized your applications? Okay, good. That's a lot of them. So what I wanted to do today was, look at a Java application developer and the life cycle of a commit. You start off doing a commit and look at each and every stage of the code change that happens, and how does that affect when it comes to producing Docker images, and how does it affect when it comes to running the container image in production and so on. So the first step obviously would be the build. So you can think of it as you're a Java application developer, you made some code changes, you've just done a commit, and that's where we start. So what's the objective here? The objective of the build from a Docker perspective would be that you come up with the smallest possible Docker image at the end of it. Why does it matter? Well, so I work out of the Bangalore office in India, and sometimes I have to deploy to IBM Cloud, which happens to be, the Houston one. And if I have a large Docker image, something like, let's say, more than 1 GB in size, it sometimes takes more than 40 minutes for me to push that image. You don't want to be doing that if you're doing a microservice development where you were doing probably hundreds of commits in a day, and you want to be able to do changes quickly and be able to deploy them as quickly as possible. So you want to make sure that the Docker image is as small as possible, not only from saving time, but also from the fact that lesser size means it is more focused towards whatever is a need, and that means lesser exposure from a security perspective as well. So there are a bunch of options starting from the operating system. So you look at Alpine, for example. It's really small operating system image. It's got just 5 MB in size. The Docker image is 5 MB in size for the operating system. So it just has muscle libc and BusyBox. It might not suit all kinds of requirements out there, but if it does, then it is really useful because it has the smallest possible attack surface. So we have Alpine builds, for example, that are supported at AdoptOpenJDK as well. And then within the JVM, we also produce slim binaries, which are basically stripped down versions of the JRE that suit cloud workloads. So for example, things like sound and desktop and configuration. And so some of the packages which are primarily not used in cloud environments are stripped out. That's the slim version of the SDK, JDK, or the JRE. And then, of course, the JLink tool itself, which is available, of course, Java 11 onwards. So instead of just talking about it, let me just go to the right shell prompt. Let me just look at this for a second. Yeah, that's the one that I want. I'm not able to see it on my laptop here, so I have to look up there. Okay, let me see how many of those. Okay, so what I have here is a bunch of Docker files. Okay, let me just see what this. Yeah, so this is the repo. So you can go to this repo and get all of the Docker files from there. I'm just going to be, so I have cloned this repo locally, and I'm just pointing to one of the Docker files in there. So this is a 2-stage Docker file. So I'm going to be using this to build my application. So it has 2 phases. One is the build phase, and the other one is a runtime phase. So these two are basically tuned or optimized for different things. So the build phase is tuned for the inner loop, the inner development loop, and so it has more layers. So each and every line in a Docker file corresponds to a layer in the Docker image. And the way, and the reason for this is that it uses caching. So for example, if there are no changes in a particular layer, you don't need to build it again. So that gets cached locally, and it just reuses the cache next time you want to make some changes down the line. So what we want to do from a build perspective is to have as many layers as possible so that you're caching each and every layer, and that helps speeden up your inner development loop, and correspondingly, you get builds faster. So if you made a change, essentially the caching will help you to ensure that only the changes that you've done are the, and I mean, those are the things that get actually built, and the rest of the things from a Docker image generation don't have to be done. So the first thing would be the from statement. So I'm just using a Maven image that we produce at AdoptOpenJDK. But equally, you can use any other Maven image, for example, that's the official Maven image or so on. And I mean, the recommendation here is that you use a standard Docker image for your Maven requirements, or whatever build tool requirements, simply because if you have something installed on your own laptop, you probably would not upgrade, or different developers will have different versions and things like that. Having a standardized Docker file with a certain version of Maven means that everybody on the team is having the same version to work with, and so there's no disparity when it comes to it works on my laptop and things like that. So once we have that fixed, the next thing would be within the Docker file you install a bunch of tools that you would probably need for your development purposes. And we all know that real Java developers always use Vim. And the next thing would be, okay, we have to go to the other side there. Sorry? Oh, yeah. This is... Okay. I have a Linux laptop, and usually never has problems, but I don't know what's going on here. Okay, so. Sorry? I can't hear you. Lights. Okay. Can we switch off the lights here, please? Okay, so the next step here is to be able to clone work with your repository. So there are two possible ways to do it. One would be to clone the repository within the Docker image itself. So you have basically a temporary Docker image that gets created every single time that you're doing the build, and you're essentially cloning your complete repository within the Docker file, within the Docker image. The second way to do it would be that you just have a cloned version that's locally available, and you just mount that and pass it to the Maven Docker image that you're using to build. So both of them are should be fine. It really depends on what is your specific need, and if there are some other options that maybe limit one or the other. In this particular case, I'm just using, I'm just cloning the repo within the Docker image itself, but both of them should be able to work fine. The next thing, which is really the most important one that I would like to point out, is that you should be able to separate the copying of the dependencies and the actual building of the application itself. So when we do something like the install dependency, copy dependencies, so that creates a separate layer. Most of the times, the dependencies don't change, and so you have, this happens just once, and you have the layer built, and from then onwards, the rest of the time that you do the build, it just needs to build the changes in the application and not have to download everything. And we all know that Maven tries to download the internet every single time, so you don't want to be redoing that step all the time. The next best practice would be that you should not have root user. So most of the times, this is something that's not very apparent. Docker uses root as the default user. And so, that's not ideal, especially because containers offer only light isolation. So we are essentially sharing the kernel from the host operating system. So if you become a root within a container, you have become root on the entire host, and you can basically play around on the host and do whatever you want. So to be able to prevent that, you have to have a user with as less privileges as possible. Of course, you can specify different operating system level privileges to Docker. So And so, for example, if you want to have sysadmin privilege, you can pass only that option to Docker. Whereas, there are different capabilities. So there's net admin, sysadmin, and so on. There are about, I believe, more than 50 different capabilities that are available. And so you should be able to create your own user and pass the specific capabilities that your application needs. So in this particular case, I'm just creating a user 1001 and switching over to the user so that from now onwards, everything that runs runs with that particular user ID. So how many of you are using Java 8? Wow, okay. Java 11? Anybody using anything newer than Java 11? Okay. Lower than Java 8? Okay, that's good. So this particular step, the jailing step, is only applicable to Java 11. And I would actually recommend, at least from a container or a Docker perspective, that you switch to Java 11. And I can show you the reason why. So this is the application that I have. It's actually a very simple application. I'm going to show it running in a minute. So it's a simple application that uses Watson APIs and gives you a web page where you can do text-to-speech conversion and things like that. It's a non-modular application, but I can still use the Java 11 compiler to be able to compile the application and get all of the benefit that jailing provides me. So jailing, as you're aware, is a tool that helps you to provide or create a custom JRE for your application. So jailing goes in and looks at all of the modules. If you have modularized your application, it looks at your module info files, looks at what are the specific dependencies that are there, and packages all of those dependencies, starting with the java.base and adding all the other modules that are needed, as needed. If you have not modularized the application, you would need to specify that manually, as I have done out here. So if you can see all of the modules that are out there, java.desktop, instrument, logging, and so on. So I've had to specify that manually because it's non-modular. But if it was modular, all you had to do was the jdeps command out there. I think it's wrapping around here. So you can see that it says, jmods. So jmod add modules and giving it the jar file. So with just that one command, it should be able to figure out all of the dependencies and add the modules that are needed. But if not, you can specify them manually, as I've done out here as well. So, just doing this, you'll see, actually gives you a much, much smaller binary than Java 8. And, you really don't have to modularize to be able to get this advantage. I've also stripped out a number of other unnecessary files that are present in the JRE, for example, the properties files, and I've removed debugging, and I've specified compression as 2, which means that that's the maximum compression, and that gives you the smallest possible size again. So the next step, this one is actually specific to OpenJ9. So this is called as the share class cache. So one of the things that we would like to do is to be able to get faster startup with applications, and especially in containerized environments. So what the share class cache does is essentially it's a ahead of time compiled code. So you run the application with these specific options. It gives you AOT code. Which is not the most optimal code, but it still is much better than having to deal with bytecode. So it gives you that in the form of a binary file, which you can then, which is separate from the JRE, and you need to copy that over to the final Docker image as well. So the combination of the JRE and the share class cache will give you really good startup time, as I'll just be able to demo that right now. So what I've done here is specified these specific options, the Xshare classes, and then I'm actually running the application in the next step there. So this ensures that when the application comes up, with those specific options, it actually creates the share class cache and it gets copied to disk. Okay, so that essentially concludes the build phase. And the next stage of the Docker file is the runtime phase. So here I'm starting off with a custom version of Alpine. So as I mentioned earlier, Alpine consists of something called as a muscle libc, and normal, either Hotspot or OpenJ9, the ones that are available at AdoptOpenJDK, or even the ones that are available with your distro, are usually compiled with glibc and not with muscle libc. So what I have here is that I'm starting off with the base Alpine operating system and installing glibc on top of it so that I'll be able to run either any version of OpenJDK essentially. The Docker file for that is available in the same repo as well. You can take a look at it. And then I do the same thing that I did earlier in this stage, add the same user ID that I had created earlier, switch to that particular user, and then copy over the actual, the application that was created in the build phase. I copy over the application, and in the Java 11 case, I need to copy over the J-linked JRE as well. And if I have the shared class cache turned on, I can copy over the shared class cache as well. So that's the second step there you see. So the SCC is getting copied as well. So that is essentially the ahead of time compiled code that was produced when I first ran the application. And of course, if I'm using the SCC, I also need to mention the, point it to where the SCC is now being copied to and the X share classes option. So, so let's actually run this application and take a look at it. Let me see. This is really not ideal. Okay, so before I do that, let me just show you these are all the images that I've already built. And you can see that the last two images here, these are the last few images. They are the version 11. And you can see that they're much, much smaller than the Java 8. So it's about 97 MB. So the J-linked JRE plus the application, it is just 97 MB in size. Whereas if you look at some of the Java 8, they are in terms of around 200 MB and so on. So the smallest possible Java 8 image, which is the topmost one, which is the slim image, where we have manually stripped out some of the classes and so on. It still stands at around 120 MB. So it is still higher than the whatever J-link produces. And then you can also take a look at the shared class cache image. That's about I think 129 MB. So even after we add the about 30 MB of the shared class cache file, it is still comparable to the Java 8 slim image. So I would say that this is really good example of why we should be using Java 11. And I mean, you still you still don't have to modularize it, but you will be able to get all of the benefits anyway. So now let's try to run this. So I'm running the plain J-linked image first, not the share class cache version. So let me just run that image. Okay, do you see all the images? I think think I need to push that a little up. Okay, so if you look at the time that it took for the application, it starts off at 7:37:24. So it took about 4 seconds for the application to come up. So now let me try to run the share class cache version. Okay, so this one, let's see, it was 7:38:07, so it took about 2 seconds. So typically you get 40 to 50% speed up with the share class cache turned on. That is, I mean, the larger the application, actually, the more benefit that you get out of it, simply because of the fact that you start with ahead of time compiled code. So just to make sure that we have the application actually running, let me just run that, access it, localhost 8080. Yep, so we have the application running. Okay, so going back to my slides. So essentially, we looked at the build phase. The goal of that is to produce the smallest possible Docker image and also have an optimized Docker file, which gives you faster inner loop, the development loop, and also smaller size of the Docker image. And then the next step is, of course, the startup and scaling aspect, which we already looked at. With the shared class caches, it typically gives you about 40% startup benefit. If you're looking for something like a serverless kind of an environment where startup is really essential or needs to be extremely small, then you can also look at X quick start mode, which is really only good for short running applications. But I mean, so if you have a long running application and you need to focus on throughput, probably this is not such a good option. But if you have a short running application where startup is what you're looking for, then I would suggest that you can look at quick start. Okay, so we looked at the startup options here. They were pretty good in the sense that we were able to get almost 100% quicker with the shared class cache. But then we have new requirements like serverless, where we are expecting startup in the range of less than a second and so on. So this is a project that I found was really useful. It's called CRIU. It's essentially checkpoint restart in user space. So this is an open source project which is maintained by the Linux community, where they've added a number of features that allow you to checkpoint. So what I mean by checkpoint is you bring up your application, and after it has come up, and done with its initialization phase, you take a checkpoint, and essentially what happens then is that you're dumping the contents of memory, the disk, and the entire process to disk, and then if you restore that particular process from disk, so you're doing away with all of the startup time, as you can see out here. So we've taken the checkpoint in the top diagram after the startup phase is finished. We've pushed the files to disk, and now we are doing a restore from that. So you're essentially reducing all of the startup time, and your startup is in terms of milliseconds or even less, depending on how much of content it has to copy from disk to memory. So it's so not only is there a significant reduction in how what kind of startup benefits that you can get, it also helps you to scale pretty rapidly, because once you take a checkpoint, the checkpointed image can be restarted any number of times, and you'll be able to get the same kind of startup benefits. So what we have done is actually, so there is a little bit of work involved here when it comes to checkpointing. So you need to be able to figure out where to checkpoint and have the Linux tool, the CRIU tool, run it at that point in time and be able to checkpoint that. So it's not the most easiest of process. So what we have done is written a number of scripts that enable you to be able to take a checkpoint for a standard stack and produce this checkpointed image, put it inside of Docker so that when you restore it, or when you run the Docker image, it actually does the restore operation. So all of this is done under the covers. So this is actually, this is something that we are working on, and it should be available in the Rhapsody project, which is an open source project. You can check that out. So that, we have a bunch of stacks that are available. You have Spring Boot or Quarkus, or you can apply it to any of that. I mean, it doesn't matter which runtime. It's equally applicable to Node or Python or any kind of runtime, because it's essentially a Linux feature. So you take a stack and bring up the boilerplate application, for example, take a checkpoint, and then create a Docker image out of that. And then when you run the Docker image, it essentially does a restore, which helps you to, so Kubernetes doesn't know, for example, when it runs the Docker image, it doesn't know what's going on. It just is just like any other Docker image for it. And we do the restore operation under the covers. And so that helps you to get that startup time and the scaling as well. So I have a demo for that. Okay, sorry about this. Oops, okay, I still have my application running. So what I'm trying to do here is set up the screen for auto refresh for every second. And if I can start my application. Okay, let's stop this one first. Oh, okay, I think I've got that. Yep, finally. Okay, so I have script here. So what this script is doing is, so I have two different Docker images. One of them is the CRIU one, and the other one is the non-CRIU. It's just a pet clinic application, and you can see that this is the CRIU version. So this came up pretty quickly. The other one is a non-CRIU one. I think it takes much longer. I had a timer here, which I was going to start. Maybe I should do that. Okay, screen is really messed up. Sorry for that. There's my timer. Okay. I don't know where my timer window, I will find that. Says it's there. Okay, maybe I should close the rest of them. Okay, so I don't want to spend too much time on that, but essentially this takes about 4 seconds for the Docker image to bring up the application. So I mean, it's not exactly a hello world kind of an application. So, but then the normal application takes around 14 seconds or so. So there's actually a significant speed up. So this is something that if you're really interested in startup, I think that that's something that you can check out. Okay. The next thing is that, okay, so now that we've taken care of build and startup and scaling, the next thing is that we have the container running. So what are the things that we can do here? The first thing is that there have been a bunch of changes that have happened in the JVM that allow it to be container aware. So what that means is that the JVM now knows that it's running inside of a container, knows the limits that have been imposed on the container, and so it automatically resizes its heap and so on, based on that. So how many of you here use -xmx in your applications? Okay, few hands. So that is something that if you have containerized your applications, I would suggest that you avoid it. And that is because, as illustrated here, we have 3 different scenarios. So essentially, what we have done here is that we have imposed 3 different limits on the containers. So, the first one is limit of 2 GB, then the 3 GB in the center and 4 GB on the other side. So essentially, this is a pretty common scenario that happens when you're running in Kubernetes clusters. The limit, can change dynamically. It depends, for example, for a production cluster, you might have a different set of limits, test QA cluster, different ones, and so on. So if you hard-coded your -xmx, there are possibilities that you might actually end up crashing. For example, in this particular scenario, the container memory limit is 2 GB, and you've specified -xmx as 2 GB. So the heap itself, if it takes up 2 GB, what happens to the native memory and the code and so on? So it has chances of getting out of memory and getting killed. And similarly, if you have a container memory of 4 GB, for example, 2 GB might be not optimally utilizing all of the memory that's available to you. So if you use -xx max RAM %, that is something that actually resizes the heap based on the limits that have been imposed. So the -xx max RAM % looks at the overall RAM. If this is something that's applicable even in the out of the Docker context, as in if you're running on bare metal, you can still use the -xx RAM %. It will just look at the overall RAM that's available on the system and accordingly set the size of the heap. But in this case, I've set the -xx max RAM % as 80, and it auto resizes it to the heap to 1.6 in this case, and 2.4, and so on, based on the limit that has been imposed. So definitely recommend using -xx max RAM % and initial RAM % instead of XMX and XMS. Similarly, the runtime.available processors, if you're using that, you don't need to make any changes because this has been now enhanced to be made aware of the C group limits on the container. So it will automatically give you the right amount of processors that have been made available to that container. We also had an option called use container support, but that's now turned on by default, so you really don't need to do anything here. Okay, so the next question that comes up is, how do I set those limits? So this is if you've been running a Kubernetes cluster, one of the things that you run into all the time is, most of the times people would not have right-size the containers. So it's a question of, I hit a problem and my container crashed, so let me just increase the RAM. And usually it's like, okay, I'm going to double the size of the container just to be on the safe side. So most of the times you don't end up right-sizing the containers. And this is a problem that we faced in a number of scenarios. And so we came up with a tool called as Cruise. It's actually been open sourced late last year, and it's now available for use. It's open and free, and so definitely I would suggest that you check it out. What it does is, so you can deploy the Cruise tool to a Kubernetes cluster, and it can monitor all of your applications that are running, and it looks at the CPU usage, the memory usage, and then gives you recommendations on what should be the optimal values for these limits. So there is something called as a vertical pod autoscaler that's available in Kubernetes, which essentially does the same thing. But the thing that we are trying to do with Cruise is that, so VPA looks at any particular pod as a black box. It doesn't really look inside that. It just looks at the CPU memory usage and gives you recommendations based on that. But with Cruise, what we are trying to do is to look inside the container to see what kind of runtime you have over there, and then suggest optimizations based on the runtime. So for example, you have Hotspot running in there, or you could have Node.js or Python or Go or any particular language of your choice. So we should be able to get metrics that are specific to that particular application, figure out what runtime you're using, and then suggest options. So for example, in the previous slide, we had things like -XX max RAM percentage. Ideally, we should be able to auto-generate those options as well. So for example, you have an application that is running, we figure out that all it needs is about 2 GB of RAM. And then, so what should be the max RAM percentage? So what should be, out of the 2 GB limit that you want to impose on the container, what should be the size of the heap? We should be able to figure that out automatically by the tool. So it should be able to tell you that, okay, your heap size should be something like 1.2 GB because you use maybe 600 MB of native memory for whatever reason, and so on. So we should be able to come up with those values along with this limits as well, and it should be able to suggest other options as well. For example, what kind of GC policy should you be using, and so on. So performance in the cloud is something that is still a relatively, I would say, untapped area where people are only now figuring out how to do performance optimizations and things like that. We hope that this tool, grows to be able to, fill those requirements. So anybody here, interested in performance tuning and things like that, I would suggest that you can contribute to the tool as well. Doesn't matter which runtime that you are looking at. We can have, for example, Hotspot specific options or OpenJ9 specific options or Node.js ones and so on. We can add that into the tool and let that give you the recommendations of the -XX parameters and so on. So definitely, you can go check that tool. Okay. So the next thing is idle awareness. So idle, especially on the public cloud, where you're being charged for the amount of resources that you're actually using. If your application is sitting idle, you do want to make sure that it's not just hoarding lots of memory. So we have, this is again something that is specific to OpenJ9. There's more information in that blog link that I've given over there. So essentially what we do is we have, inbuilt into the JVM, being able to detect if the application goes idle. And this allows the JVM to give back any of, basically compact the heap, run a GC, compact the heap, and free up as much memory as possible. And then it gives back all of the free memory back to the operating system. So the cloud provider who's tracking the usage should be able to see a drop in the actual usage and charge you accordingly. So you would definitely be saving money with when you use that. It really depends on, of course, how much memory you can free up. It depends on the application that you have and workload characteristics and things like that. But this is a pretty useful feature, considering that it provides some monetary benefits as well. So yeah, the only thing I would mention is that those are the specific options that you can use to be able to turn that feature on. And the last thing is in terms of debug ability. So, so again, this is something that is not really ideal, as in, we saw in the first step that we had to strip everything out to be able to make it the fastest possible, or, make it come up, as quickly as possible and things like that. But that also meant that we are taking out a lot of the debug info and things like that. So that's really, to be frank, not so good from a debugging perspective. But one thing that does help is, so we have something called as a OpenJ9 diagnostic MX bean. So this is also available in Hotspot. I think it's just called as the diagnostic MX bean. So it has a bunch of methods in there that allow you to be able to connect. Of course, it's just an MX bean, so you should be able to connect to that container you're just using a JConsole. And once you've done that, you can use these methods to trigger a dump. So you can also change the dump options. So for example, the idea here is that you don't need to rebuild the whole Docker image with specific dump, -x dump options, just for you to be able to trigger that dump. So you should be able to do that on the fly by using JConsole, connecting to that container, and then using this MX bean to be able to trigger a dump and even set whatever dump options that you need. So I think that's a pretty useful feature. And the last thing is in terms of the Java core. So this is something I think, again, which is specific to OpenJ9. So this is a text file that gets generated after every dump, which consists of all the information, whether it is to do with the system or the number of the threads within the JVM and so on. So it is a comprehensive text file that consists of all of the metadata about the JVM that was running. So we've added a section in there which dumps information about the container awareness as well. So you're able to figure out whether you're running inside of a container, and then what kind of limits that were imposed on it, and so on. So all of that information is now added into the Java core. So that should help you with the debugging as well. So yeah, that's pretty much all I had. So these are all the links. So what essentially we saw was look at the different phases of typical developer lifecycle of a commit, and look at each of those and see how we can optimize the application and the JVM to give you the most optimal performance and whatever characteristic that you're looking for from a container perspective. All of the Docker files and the demo is available on the first link. Cruise is the tool that I mentioned that allows you to right size and optimize your containers. CRIU, as I mentioned, it's the open source project. It's a community that allows you to checkpoint your applications, do check that out. And of course, AdoptOpenJDK. So you should be able to get binaries as well as Docker images from Adopt. So that's pretty much all I had. Thank you.